Hey everybody, welcome back. Mr. G here again. What we've got now is another example of Norton's circuit. This one has a twist, something a little bit different than we saw in the first one. So here we've got resistors 1, 2, 3, 4, and 5, and our load resistor is here. Again, what we're going to be doing is converting this circuit into Norton's equivalent, which is based on a current source. And then we have two resistors, R Norton, and then the load resistor in parallel. So we've got this example. What I'd like you to do is go ahead and pause the video, see if you can solve it by yourself, and then we're going to come back and solve it together. So go ahead and pause the video now. Hey, welcome back. Hopefully that worked out for you. So we're going to come up with our solution here together, and then you're going to see if it actually matches yours. So we're going to calculate I Norton first this time. Last time we actually calculated the resistance first. This time we're going to calculate the current first. So again, what you want to do is you want to recreate the original circuit. So here's the original circuit. And again, you do this so that you can actually draw and do whatever you need on the copy. So you always have the original to go back to at the end. So here we go. This is RL at 10K. We got 4K, 5K, we got 3K, 2K, 1K, whoops, 1K, yep. And we have 14 volts. There we go. Now, we're going to calculate Norton's current. So our procedure is first to remove the load. What do we do with the load when we remove it? We put it right here. So then we take this and we say 10 kilo ohms right there. Get it out of the way. So we're going to remove it from the circuit. So we're going to redraw this circuit. So we got 1K, 2K, 3K, 5K, and then we've got 4K here, and this is where the load was removed from. So, and we take this and put the volts there. So, we remove the load. Where we took the load from, we mark it A and B. The next procedure is to make a short circuit from A to B. Here's where it has a little twist. When I put a short circuit from A to B, it actually gets rid of this resistor. Because if you have a short circuit, something with 0 ohms in parallel with 4K, the end result is 0 ohms. So, this resistor is not here now. So once we do that short circuit, if we are able to find the current through that wire, that is I Norton. So let's take a look at that again. Once we remove the load and short from A to B, everything in the circuit that is in parallel with that short is theoretically removed from the circuit, because all the current will go this way and none will go that way, or next to nothing. because current likes to take the shortest path, or the path of least resistance. So it's like this is not even there. This is a short circuit. So that means the voltage drop from this side to this side of a wire is nothing, 0. So this resistor is completely out of the question now. So what we have left is this. So that circuit turns into this one. This is the 1K, this is the 2K, this is the 3K, and the 5K. And this is our wire. And this is where we want to see the current. And that is I Norton. So in this example, we are actually left with a very, very simple series circuit. So we got 14 volt supply. This current here is actually our I total. So I total will actually flow through that wire. So again, I Norton is equal to I total. And in this case, it's V total over R total, which happens to be 14 volts over whatever. So we need to find our total. Our total is 1K plus 2K plus 3K plus 5K, and that works out to be 11 kiloohms. So our total is 11 kiloohms. So 1 plus 2 plus 3 plus 5. 1 plus 2 plus 3 plus 5, 11K. So our I total in that circuit is 14 divided by 11K. So we got 14 volts divided by 11K equals 1.27 milliamps. So 1.27 milliamps. That is I total. And for this case, that is I Norton. So what we're going to do is we're going to go back to the original. Here we go, and plug that value in. So I Norton is 1.27 milliamps. All right, so we go back. So now we're going to calculate R Norton. So again, let's get rid of that. There we go. And now we're going to calculate R Norton. Remember, I Norton calculation has nothing to do with R Norton calculation. Always go back to the original circuit. Always go back to the original circuit. I can't say that enough. This calculation has nothing to do with this calculation. So always go back to the original and follow the procedure from the original. So the procedure for calculating R Norton, first thing is remove the load. So we go back, that's 5K, this is 1K, 2K, 3K, and this is 4K. Here's where the load was. Okay, so we remove the load. We mark it A and B. The next part of the procedure, short out the power supply. Now you want to find the resistance from A to B. That resistance is equal to Norton's resistance. And in this case, you have, looking from A to B, you have 4K, so 4K, in parallel with this loop. So 4K is in parallel with this loop, and that loop is 5K plus 1K plus 2K plus 3K. So again, 5K and 1K and 2K and 3K. So this loop here is in parallel with the 4K. So let's figure that out. So 5, 6, 7, 8, 9, 10, 11. So we end up with 4K in parallel with 11K. And that will become the resistance from A to B, which is also Norton's resistance. So again, two resistors in parallel, so we can figure this out fairly simple. So we got 4,000 times 11,000 equals, and divided by 4,000 plus 11,000 equals 2.93K. 2.93K. And how do we know that that value is a good approximation? We know that this value has to be less than both of those. So therefore, this could be a very good answer. So according to this calculation, our Norton is 2.93 kiloohms. So we go back to our circuit here, and we're going to plug that in, 2.93 kiloohms. So if all of our calculations are correct, the current through that resistor and the voltage across that resistor must be equivalent to the current through that resistor and the voltage drop across that resistor. So let's just work on this one by itself because it's a simple calculation. So first of all, we need to find our total of this little circuit. So our total of that little circuit is equal to 2.93K in parallel with 10K. So we're going to figure out that little value there. So we got 2.93K times 10, 1, 2, 3K equals divided by 2.93K plus 10K equals 2.266. So this becomes 2.26K. So does that value look good to you? That value has to be less than any of those, and it is. Now remember, there are other ways that you can solve this. You can do the 1 over formula if you like. So you can actually say 2.93 K, and you can do the 1 over plus 10K. 1 over equals 1 over 2.26K. Okay, so lots of ways to calculate it, completely up to you. And again, your calculator might be different than mine. You might have different buttons and so forth. You have to get used to doing it your calculator's way. So now that we have our total of this, we can use the current divider. So the current divider is going to say that I through RL is equal to IN, so that's that total current leaving the source, 2.26K over 10K. So we've got 2.26 divided by 10 equals times 1.27 milliamps. So the current, the current through the load in this case is 0.287 milliamps. So the load current here is 0.287 milliamps. And if we wanted to, we could take it and multiply it by 10,000 and find the voltage across there. So the voltage across the load is 2.87 volts. So now let's see if that's all true. We're going to go back to our original circuit and we're going to solve the current going through that resistor and the voltage drop across it. So this is a very simplified circuit by itself. We have 1, 2, 3, 4 resistors in series along with this one. So we can actually use the voltage divider very, very simply to figure out what the voltage is here in that circuit. So the first thing we need to do is we need to figure out what 4K is in parallel with 10K and replace it with a equivalent resistor right there. And then we could use the voltage divider. So let's just say that this is A and B and we're trying to find that voltage from A to B. So easy thing to do is to figure out what 4K and 10K are in parallel and replace it with one little resistor there. So we got 4K times 10K is equal to divided by 4K plus 10K equals. So this resistor that's equivalent to those is actually 2.86K. So now we can redraw that circuit and swap in that value. So this is 14 volts, 1K, 2K, 3K. This now is 2.86K and this is 5K. So, simple little circuit. Now we can easily find our voltage across this resistor here by using the voltage divider formula. So the voltage divider formula, so I'm looking at here. So the voltage across that resistor, and we'll just again mark this in A and B. So the voltage from A to B is what we're looking for. A to B is equal to the voltage total, which is 14 volts, times 2.86K, so that's the value of that one, divided by our total of that circuit. So our total of that circuit, we've got 1 plus 2 plus 3 plus 5 plus 2.86. So that works out to be 1 plus 2 plus 3 plus 5 plus 2.86. 13.86K. So 13.86K. So we have 2.86 divided by 13.86 equals times 14 volts. 2.89 volts. Okay, look at that. We take 2.89 volts and we're going to divide it by 10K, divided by 10K on the original circuit, and we get, for the current, so I of the load is 2.89 volts divided by 10K is equal to 0.289 milliamps. Look at there. So there is our proof that what we calculated as Norton's equivalent matches the original with respect to the load. Again, we're looking for the load current. The load voltage must be the same as the load current, load voltage, in order for these things to be equal. So again, here is our procedure, our simple calculation. This is our final result. So again, if you're looking for some more help, you can find in chapter 8-6 of the textbook. So our textbook is Principles of Electric Circuits, Conventional Current Flow by Floyd and Bakla. I hope that this answer matches your answer. So, I hope this helped. Everybody please take care, stay safe, and we'll see you again next time.